put in. So today I want to talk about CH containing functional groups. And in other words, I want us to be able to know how to identify alkane groups and alkene groups or fragments within molecules. Arene, in other words, aromatic, alkyne. And one of the pieces of philosophy that I'm going to try to take, particularly as we get to certain functional groups, is to start to look for patterns here. Because it's not so much about tabulating peaks, it's really about being able to read spectra. I'll want to talk today about oxygen-containing functional groups, and we'll go through alcohols, aldehydes, ketones, esters, acids, carboxylic acids, of course, acid chlorides, and let's say acid anhydrides. Obviously, there are other functional groups, and I'm just picking ones that I think are particularly important. Some of the features I hope we'll get a chance to talk about today, if not today, tomorrow. More about ring size, which I think is really cool in the case of cyclic ketones and esters. Conjugation and understanding principles involved. Inductive effects. And probably not this time, as a matter of fact, certainly not this time. We'll talk about nitrogen-containing functional groups and probably talk about amides, amines, ammonium salts, maybe nitriles. Nitriles are another one that IR, I think, really shines for identifying the maybe nitro compounds. So one of the things I'm going to urge you to do when you look at an IR spectrum is really to learn to read the IR spectrum. So let me give you my take, because part of reading is not just sitting and tabulating every peak, it's knowing what's important. So when I look at an IR spectrum, generally in my mind's eye, I think from about 4,000 to about 600, and probably, of course, these are centimeters to the -1 wave numbers, that reciprocal waves per centimeter. And probably also in my mind's eye, I end up drawing a line at 3,000 wave numbers. And I think this really ends up dividing the spectrum into some important features. So if you have an IR spectrum, maybe you see something like this. You're reading in, if I'm going to label my axis, of course, you're going to have %T, and of course your spectrum is going to look something like this. So you see some peaks and some stuff over here. Now, the region over here from 1600 to about 3600 is the functional group region, and that's generally what I look at. There's information to be had in this region from about 1400 to about 600 wave numbers. That's the fingerprint region. If we have a chance, maybe on Wednesday we'll take a look at how you can find aromatic substitution patterns from here. I think in one of the homework problems, there's the textbook, by the way, take the time to flip through it. It's got very nice appendices. They're extremely useful. One of the appendices, for example, will give you some correlating peaks to be able to figure out whether an alkene's, what the substitution pattern is on an alkene, whether it's terminal, whether it's cis, whether it's trans. Anyway, so generally my eye will sort of be drawn to this region above 1600. I'll look for carbonyls. I'll generally look at this region just above 2000 because normally you don't expect anything there. If I see anything there, it's going to send up a red flag that there may be something interesting. We already talked about alkynes. Generally, I won't pay too much attention to this region right below 3000. But there are a few things that can show up here at about 2820 and 2720 that can be indicative of an aldehyde if you have the right sort of carbonyl peak. Things down from 3000, of course, might clue you into alkenes and aromatics. And then over here, and particularly over here, you can get clued into carboxylic acid. So it's really this issue of being able to read the spectrum, I think, that's so key in being able to get some useful information out of IR. One of the things, it's not just the positions of peaks that counts, it's their relative intensities, and that can clue you in a lot. So for example, carbonyls and alkenes, C double bond C, both show up in the same region, but they have different appearances to them. So for example, a carbonyl CO is generally strong. And that's going to be usually strong relative to other peaks. But again, part of that is what fraction of the molecule is the carbonyl occupying. If you have a ketone with 6 carbons in it, you've got a lot more carbonyl groups in that path length than if you have a ketone with 60 carbons. So your ketone peak, your carbonyl peak is going to be stronger in smaller molecules than in bigger molecules. Carbon-oxygen single bonds, anything with a big dipole moment in general, not always, but in general, has strong peaks. So anything where you have substantial differences in electronegativity between two groups. Peaks that are often weak or moderate are compounds like alkynes, carbon-carbon triple bond stretches, alkene, carbon-carbon double bond stretches of various sorts, say terminal alkenes and internal alkenes. And we already talked about if there's no change in dipole moments, so if you have, say, an alkyne with 2 alkyl groups on the end, you're probably not going to see, or almost certainly won't see, the carbon-carbon triple bond stretch. If you have an alkene that's tetrasubstituted, you're probably not going to see the carbon-carbon double bond stretch. So let's say usually not seen. Internal alkenes, internal alkynes. We talked a little bit when I was talking about methylene groups, and I talked about the asymmetric stretch and symmetric stretch. We talked a little bit about CH groups. CH stretches are generally very sharp. So things that might clue you in, as I said, alkyl generally not that informative. But usually they fall between about 3,000 and about 2840 wave numbers. And if you're good, you really should be able to draw a line at about 2840 in the spectrum, because as I was saying, aldehydes can have little CH stretches and a Fermi resonance that can clue you in. Alkenes Arenes, aromatics if you prefer. Generally, we're talking about 3,100 to about 3,000. And again, you're going to get corroboratory peaks. First of all, NMR will also be useful, but you're going to see patterns. For example, aromatics will have a series of bands from about 1650 to about 2,000 wave numbers that can clue you in. Alkenes, generally you can see the carbon-carbon double bond stretch, and that's generally pretty sharp but not so strong at about 1640 to 1670 wave numbers. Alkynes, if they are terminal alkynes, of course you have a CH group, that tends to stand out. So it'll be at about 3,300. And as I was saying, they're generally very sharp. So alcohols also show up at about 3,300. But the pattern recognition is going to be completely different because an alcohol is going to be a broad band. An alkyne is going to be the sharp band. And as I said, if you are able to see the CC triple bond stretch, it's somewhere just below 2,000, depending on the exact substitution, about 2,100 to 21 to 2,260. And again, if you just see something in that general region of about 2,000 to 2,500, it should clue you in that there's something unusual. Aldehydes, as I said, the CH stretch of aldehyde shows up, and you get two bands. What happens is there's an inactive band. One of these two bands, I believe it's the 2820, is the CH, and the other one is an inactive band that essentially gets pumped by it that's called a Fermi resonance. And then that'll go along with your carbonyl, so you'll be looking in that region around 1700 is going to clue you in, let's say about 1740 to 1720 would be typical for an aldehyde carbonyl. It could be a little bit lower if there's some conjugation there. Let me put up some examples here just so we see what these guys look like. And let me get this handed out. So with this particular class, what the best way is to get these handed out, but we will figure. There'll be lots of handouts in the class. My recommendation, by the way, is get a loose leaf binder, or else get good at sort of organizing the handouts. Here, let's see, I have a few extras. Let me send some more down here. We'll be using transparencies a lot for discussion sections where really there's no substitute for looking at stuff, which of course you could do with an LCD projector, but also marking on stuff. So when you're up here, and everyone I hope is going to have a chance to be up during our discussion sections, it takes only minor skill, but you get in the habit of not standing there with your shoulder in the beam. All right, so let's just take a look at the first one. What is this first one? We'll just look at the first two right now. What class of compacts is the first one? The first one here. Alkene. So okay, great. Actually, I'm hearing exactly the sort of stuff that I like to be hearing here. So I've heard carbonyl, aromatic, and alkene, and we can actually take a very, very good guess. This peak here obviously stands out. Remember, I said draw a line in your mind at 1600. So it doesn't look like a carbonyl. Typical carbonyl is going to be a little stronger and a little bit fatter. Looks like an alkene. This should clue us in. So I'll just pick some numbers here. I'll just write 1642. And here we're at about 3080. Now, if I had to guess, and fortunately you will probably get other data, but if I had to guess, I'd say what we're seeing here, usually with an aromatic, you'll have a series of small, very weak bands. For like a phenyl group, it'll be about 4 of them between 2000 and 1600. And this doesn't look like anything like that. You'll usually see more CHs for phenyl below from about 3000 to 3100. So this is indeed an alkene. Now, one of the reasons I'm not putting as much emphasis on the fingerprint region, so here, for example, you get some CH bends, is as you get to bigger molecules, the fingerprint region is going to become more and more complicated and less easy to read. And, you know, part of the problem of the pedagogy of IR spectroscopy, it's a relatively mature area. It's been around largely, you know, since the 1950s and used as a tool by chemists. But the molecules that we study have gotten bigger and more complex, and people, for pedagogical purposes, still tend to look at small molecule examples. This is a small alkene, maybe octene or something. But as you get to larger and more multifunctional molecules, this region gets harder to read. All right, so what else do I want to do right now? What about the second example here?
That's not bad.
Alkyne, yeah, terminal alkyne. And so some of the things that we see here, there's this band at about 3310. There's another band at about 2119. And the band at 3310 is quite sharp. And so that's very characteristic of an alkyne. And so yeah, indeed we have an alkyne. This region at 2000 jumps out at me and says, yeah, at about 2000, 2100, there's something jumping out. Alcohols in general will be broad if you have an alcohol that's not hydrogen bonded. In pure form, alcohols tend to hydrogen bond to each other. If you have them very dilute, they tend not to hydrogen bond, but then they tend to be about here over at about 3400, 3500. Silanols can even be a little bit further. If the alcohol is very sterically hindered, like a tertiary alcohol, you'll have less hydrogen bonding than if it's more sterically hindered, like a primary alcohol. And so you may see a monomeric band. Remember, the monomeric bands are going to be about 34, 3500. All right, I want to go back to scratching out some more examples on the blackboard. Let's see. All right, so alcohols, as I said, your OH, if you're neat is just another way of saying not dissolved in a solvent, for example, as a film on a salt plate, or a KBr pellet. Because in a KBr pellet, if you are dealing with a solid or a neutral mol, you're going to have particles of your alcohol that are hydrogen bonded together, where the molecules are hydrogen bonded together. But usually you'll see a band at about 3300, it'll be broad. And on the pattern recognition, again, if I'm drawing these 2 points in my mind's eye, say the end of the spectrum at about 4000, I guess the examples I have here may run to 4600. What you're going to be seeing is a band that sort of picks up at about 3600 and comes down maybe somewhere around 3000, and then of course you'll have some alkyl stuff over here. So you might say, well, it's 3300, but your look and in your eye you're seeing this thing pick up at about 3600. So you're going to see this pattern. And this will be different than a carboxylic acid that may pick up around here, but is going to go down around here, and it's going to be really, really ugly. as I said, I'm not putting so much emphasis on the fingerprint region. You can sometimes look for corroboration. CO single bond, we talked about it last time in comparison to a double bond when we were talking about a harmonic oscillator and frequencies and the bond strength for single bond versus double bond. So usually somewhere between about 1,300 and 1,000, but I'm going to say often buried in other stuff. And again, even more so in bigger molecules. All right, let me take an example of an alcohol just so you can see something apart from my little pigeon drawing over here. And this is a small alcohol. Small alcohol, so we have this band at about 3,300. We have, here in this small alcohol, you can see your CO single bond stretch. And again, the main thing I'm looking at is that this is sort of picking up and coming down. All right, any thoughts or questions on this one?
What was C? Oh, sorry. What was C?
C are a number of, I believe, certainly in this region you have your CH bins. Remember we talked about methylene groups and we said there's one at about 1380 and another at about 1460. So certainly a big part of what you're seeing here, because this is going to be a small chain linear alcohol, big part of what you're seeing are your CH bins there. Remember, yeah, so the CH stretching modes are much stronger, much higher frequency. Those are at about 3,000. The CH bending modes are at about 1360 and 14, about 13 to mid-13s to mid-14s. And you have the asymmetric, the in-plane and out-of-plane bending. There are actually things you can discern in this region. And again, there are better ways to do it in general. But in this region right here in the CH bending region, you can actually determine the difference, for example, between a single methyl group and an isopropyl group. And again, some of that is coupled vibrations, where an isopropyl group gives you a special coupled vibration that you can pick up. But there are probably better ways to do that, and in big molecules, things are just awfully crowded. The carbonyl region from about 1650 to about 1850 really should talk to you. The carbonyls are going to be strong. I'll take ester, aldehyde, ketone, carboxylic acid, and amides as 5 groups that are really important. And I've written them in general in order of decreasing frequency. So we're talking for this particular group with sort of normal, non-unusual carbonyls, let's say 1750 to 1650. And we're generally talking about strong. So esters, generally, we're talking about 1750 to 1735 if there's nothing to perturb it, like conjugation or strained rings. Aldehydes, in general, we're talking about 1740 to 1720. And as I said, you can often pick out the CH stretch in the Fermi resonance, if you look at right on the edge of the region at about 2800, right at about 28, 20, 27, 20. A plain old vanilla normal ketone, we're typically talking about 1725 to 1705 wave numbers. A carboxylic acid, again, without any sort of conjugation or anything special, we're talking about, say, 1725 to 1700. Carboxylic acids love to hydrogen bond. And you get these very nice hydrogen bonded dimer stretches that generally produce broad non-specific CH stretches that, as I said, will cover that whole region from about 3,500 to about 2,500. Amides, typically we're talking a little bit lower frequency, and I'll talk about why in just a second, but let's say about 1690 to about 1750. And we're talking primary amides that have 2 NHs, secondary amides that have 1 NH, and tertiary amides that have no NHs. So, as I said, carboxylic acids are one of the ugliest things that you're going to see in the IR, and their ugliness really makes them stand out. It's kind of like a pug dog. You look at a pug and you say, oh, that's so ugly, it's almost cute, as a matter of fact. So you look at a carboxylic acid and you just sort of have this misformed, misshapen band, maybe with some lumps and some CHs. Maybe I've over-exaggerated a little bit, but suffice it to say it's a little bit lumpy. And then you're going to see your carbonyl standing out, probably a little stronger for this example. Let's say it's 1725 to 1700, unless it's conjugated, in which case it'll be lower. And then some stuff in the fingerprint region. And generally, my eye kind of catches a shift in the baseline at about 3,500, and it catches it coming down at about 2,500. If you've got a big molecule, it's going to be a lot smaller band. This is one of the reasons I'm not a huge fan of KBR pellets. KBR pellets, it's really hard to get your KBR dry. And when you get to bigger molecules, being able to figure out, is that just a little bit of adventitious water in my KBR? Is that an alcohol? Is that a carboxylic acid? Can be tough. As I said, aldehydes. So I'll just write, let me write some text here. I'll say 3,500 to 2,500. And I'm going to say broad and ugly. For an aldehyde, just to show some corroboratory stuff, let me draw out the same sort of pigeon spectrum here from about 4,000 to about 3,000 to about 600, about 1,600. I'm going to make this a little bit bigger so you guys in the back can see it. So usually what will happen is kind of right on the edge of things. It's really loud, so carbonyl. Right on the edge of things, you'll probably be able to, if you look hard, pick up a band at about 2820 and a band at about 2720. And then this band at about 1740 to about 1720 again, unless it's conjugated. So that can help you put you in. Now, if I had an IR spectrum like that, the next thing I'd do is look at my NMR spectrum and see is there a peak from about 9 to 10 parts per million that I'd expect associated with an aldehyde. I'll give you a moment to finish up sketching this. All right, so let's take 1 moment to read couple more spectra here. What is this third one? So we have aldehyde. Aldehyde. Everyone agree?
How would that differ from a ketone spectrum?
So if I'm looking here, I really don't see much of anything over here. So I'm suspicious on an aldehyde. Our peak here, and you should get good at reading analog. I know everyone is into digital mindset, but learn to take a scale and go, okay, 1700, 1800, these tick marks are 20. So I go 10, 20, 40, 60, 80. So that's right at about 1715. If the number digitally was 1717. So it's a little low for an aldehyde. We're shy on anything over here. And again, you really can draw in you can with a pencil draw, and you notice here the tick marks are closer together, but you can draw a line right here is the line at 2840, and there's just nothing that looks distinct. They're just little teeny resonances. So there's really nothing to speak of here at 28, 20, 27, 20. So the data for common carbonyl compounds is low to be an ester. We don't see a corroboratory CO single bond peak, but you know, it's impossible to tell anyway. But it's low to be a normal ester. It's a little low to be an aldehyde. We don't see that sort of big ugly associated with a carboxylic acid. It's high to be an amide. We don't see any substantial NH. This type of thing is not uncommon. That could just be a little bit of water in your sample, but this little bit is not uncommon. And that really puts this at a ketone. Just sort of a simple and straight ketone. Last one, carboxylic acid. That one screams carboxylic acid. We've got this carbonyl at about 1710. We've got this big ugly over here at about 2520 to 3500. And so if you're on top of things, like that, you're in pretty good shape. All right, I want to talk about some other effects here. So let's talk about effects of ring size, and then we're going to talk about some conjugation and some other effects. So, okay, so remember, a normal ketone is about 1715 wave numbers. A small ring is going to bring it up to higher wave numbers. So a cyclopropanone is at about 1825 wave numbers. Cyclopropanones generally aren't stable. They generally undergo ring opening. But on the other hand, cyclobutanones are. Cyclobutanones are at about 1780. Cyclopentanones still have a little bit of ring strain. It's at about 1745. And as I said, by the time you're at cyclohexanones, you're right back where you'd expect to be, about 1715. So what's going on? What does it mean that the frequency is higher for small ring? Stretches faster, which means the bond is stronger or weaker? Stronger, right? A spring with a very stiff spring vibrates quickly. A very slack spring, a very weak spring, vibrates slower. We already saw that trend. The CO single bond has a stretch at about 1100. The CO double bond has a stretch at about 1700. Remember, it's that root K over mu term, that root force constant over reduced mass. So if you increase from 1715 to 1825, that's a good bit stiffer spring. So that means the carbonyl bond is stronger or weaker?
Stronger.
Stronger. Is that surprising? It is surprising. How can that be? Carbon-carbon bond could be weaker. It's a good way to start thinking about it. Do you have some specifics?
I was just going to say, since the ring has more strain and more prone to break open, the carbon-carbon bonds in the ring are weaker, the stronger.
We're on track here.
Does that contribute to the P character of the
P,
CO bond?
yeah, so let's think about P character. So what sort of orbitals, if it were a perfect world, what sort of orbitals would you use to, well, what sort of orbitals would you first use to make up, say, a regular normal 109.5 degree carbon? sp3. If you're going to go to a strained ring, do you need more S character or more P character in the carbon?
What S character?
In the carbon-carbon bonds. Which way are the P orbitals oriented? So the P orbitals would be at right angles, right? So if you just use P character, you could make this. Now, in fact, you don't, but you put in more P character here, which leaves what? More S character. And which is lower in energy? Which forms stronger bonds? S. So it's sort of counterintuitive because you think strain, oh, that should be bad, and yet it goes in the opposite direction. When you think it through, it actually makes sense. And we're going to see this coming up as a trend in a couple of times. And as I was also saying, this should talk to you. If you have, NMR is not great for telling a cyclopentanone from a cyclohexanone. But if you get these types of wavelengths, it's going to be telling you something's going on. That's why when I got my beta-lactone that I was talking about last time at 1820, even just a perfunctory glance at the spectrum said there's something going on in a way that no other technique was going to say. And just as in the case of the ketones, in the case of the esters, your numbers go down with less strain, and by the time you're at, so this is a beta-lactone, gamma-lactone, and delta-lactone, by the time you're at a delta-lactone, you're right at a typical ester position, right at 1735 wave numbers. Now remember, when you're carrying out reactions to make molecules, you're not just corroborating what you think you've done, you're actually asking the question. I had a hypothesis, if I mix this stuff, I'm going to form this. And sometimes you get a surprise, and it teaches you something. So let's talk about, so that's ring size, and that is something that IR really shines at. Let's talk about something else. Let's talk about conjugation. So remember, a normal ketone is about 1715. If we go to cyclohexenone conjugated, we're at about 1690 wave numbers. So does that surprise us, or does that make sense?
That makes sense.
Makes sense. Why does it make sense?
Because of the conjugation, the carbonyl bond has more single bond character, so it should be lower than
Conjugation makes the carbonyl bond have more single bond character, and it should be lower in wavelength, lower in frequency rather. So you can write a resonance structure and it dominates the reactivity for alpha beta unsaturated compounds. Remember, they're Michael acceptors. Nucleophiles like to add into the beta position. The beta position has a delta positive on it. Of course, we know at the graduate level, it's not that it's one structure and the other, and resonating between them, it is simply both structures at once. This is a representation of the molecular orbital character of the molecule. And so the molecular orbital character of the molecule says it's not quite a full double bond. It's a little bit weaker. It's, 90% double bond, 10% single bond character or something to that effect. All right, so just so I can play with your minds, then why is it, if you look at least certain compounds like this, we'll see, let's say, a band at, a little bit weaker, a band at 1690 and a band at 1640 for an alpha beta unsaturated like this. Not exactly, but kind of, sort of. What other stretch do we have?
The alkene stretch.
You have the alkene stretch. And in fact, so you have your CC stretch and your CO stretch, and in fact, because your alkene is really polarized, right, the polarization leads to stronger stretches. So because it's really polarized, you have a bigger dipole moment, or more specifically, a bigger change in dipole moment as you vibrate it. It'll be kind of strong. All right, one last category to play with, and that's electron withdrawing groups. And this is another one where IR really shines, because let's say you're making an acid chloride. Telling an acid chloride from a carboxylic acid by NMR often isn't that easy. But by IR, it's like falling off a log. So an acid chloride shows up at about 1820 wave numbers. And just in general, if you have any sort of electron withdrawing group, remember, a normal ketone, say, would be at about 1735 or about 1715, an ester would be at about 1735. So this is often a region that should be making you stand up and pay attention. So what does that say about the carbon-oxygen bond? Stronger bond. Again, counterintuitive until you think about it for a second. If the electron group, withdrawing group, is pulling electrons away, you can think of a second resonance structure, what you can call a non-bond resonance structure. Like so. And that non-bond resonance structure is going to have carbon-oxygen triple bond character. There's not much of this contributing. This is just a representation of the molecular orbitals in the molecule saying that you're pulling electron density onto the electron withdrawing group. But it's enough to shift the carbonyl group a little bit. If you go to an acid anhydride, an acyl group, of course, is electron withdrawing. Any group that's an acylating agent, any group that's prone to attack by a nucleophile, especially a prone, is going to be a carbonyl with an electron withdrawing group. So, right, a nucleophile, a weak nucleophile like water or an amine is going to react very rapidly with an acid anhydride or an acid chloride. And we see a band again at about 1820. And we see another band at about 1750 wave numbers. What gives here? 2 carbonyls, and that means asymmetric and asymmetric stretch. So you get a couple vibrations. Even if the carbonyls aren't in the same molecule in certain protein structures where you have carbonyls near each other, you get vibrational coupling that splits your carbonyl stretches into 2 frequencies. All right, last example for today. Take an amide. Generic amide, and I already gave you the numbers, 1650 to 1690 is sort of typical. What does that say about our carbonyl stretch?
Weaker.
Weaker, and
It's electron donating. So it's kind of the opposite of what you have just above. You can have, like, it's donating more, but it's like kind of a single bond character.
so you can write this resonance structure, and that's an interesting conundrum of various groups here, in that all of these groups with lone pairs can be donating by resonance, but they can be inductively electron withdrawing. And in some cases, one wins out. In some cases, the other wins out, right? Nitrogen and chlorine are both electronegative. But the big difference is nitrogen is in the same row of the periodic table as carbon, so you get good pi donation. You get good overlap. And nitrogen, the donation, wins out. Whereas chlorine, although about equal in electronegativity to nitrogen, is down a row, and so you get a big sigma electron withdrawing effect and not so much pi donation effect. So, and in this case, you simply have, say, compared to an ester, where in an ester, this oxygen can donate into just one. In the case of an anhydride, that oxygen has to donate to 2, so you end up with more electron withdrawing. Anyway, this is probably one last thing, and then I'll wrap it up. One more. All right. Last thing. All right, so we said a normal unstrained ester or lactone is at about 1735. If I go ahead and take an unsaturated lactone where now we're not conjugated with the carbonyl, but conjugated in the other way, conjugated with the oxygen, we move to 1760. And again, you can think of this as a resonance effect. You can write a resonance structure like so. To put it another way, this is a lactone of an enol ether. Enol ethers are electron rich at the position here, basically. If you have an electrophile, it's going to attack here. And you see that in the IR spectrum. All right, so that probably sums up everything I want to say about CO containing functional groups. We'll pick up next time with nitrogen.